This. Yes? Okay. A lot of room on this side. Okay, so let's start then. There is room on this side. You can just come in. So I want to start by reminding you where we were last time. We defined learning. We talked about an input space, X, capital X on your left. Think about it as email messages. We talked about space of outputs, labels. Think about them as the names of my folders. And we are after a model, G of X, that can take each X in the input space and map it to this Y. That's our problem. Of course, we need to make a lot of decisions here, and that's some of what we're going to talk about today, but we kind of set the stage for what we are talking about. And then we move to give some examples. We played with this toy example of 4 features, input space of size, or instance space of size 16, and we talked about whether learning is possible, and concluded, and this is really the one first important lesson in this class, that it's really only possible if you make some additional assumptions. And one key assumption that we are making And we'll see that sometimes we're making it explicitly and sometimes implicitly, but we're always making it, is the assumption of a hypothesis space, the space of functions that our learner is allowed to consider. So we talked a little bit about this, gave some examples, and then we show that under some assumptions, if we guessed right, we can find a consistent hypothesis, not the only one, because several of you gave other suggestions that on the face of it were as good as my suggestion here. I also said something just because I know that some of you are interested in neural networks, that this is really a neural network, even though when I show it this way, maybe it doesn't look like that. So that has two lessons. One is that the same function could be represented multiple ways. I can represent it as 2 out of these 3 variables, but maybe I can also represent it as a neural network or a linear function, and we're going to get to it today. And the other lesson is that this notion of hypothesis space could be sometimes tricky. So let's see. So with that in mind, we talked a little about the view of learning. Really, what is learning is some kind of a removal of the uncertainty that you have. You make some guesses, you say, these are my options. This is the family of functions that I'm after. And then you use the data in order to remove the uncertainty, which means you have to guess right, and you could be wrong. Because if all you do is look at the data, and it has to be a limited amount of data relative to the possible inputs, the number of possible inputs your problem can take, you can be wrong. So there's a lot of questions that we're going to ask as we go. When are we going to be wrong? How do we make sure that we're not wrong too often? How can we quantify this? The important thing is that it gave us, and I think this is where I ended, or maybe one more slide last time, is it gave us strategies for machine learning. So we can either develop flexible hypothesis spaces that are very expressive, decision trees, neural networks, nested collections of functions, or we can develop representation that are really a restricted hypothesis space, like different grammars, probabilistic representations, stochastic models, and so on. In the first case, because, as we'll see, neural network and decision trees are very expressive, we are going to use algorithms as a way to constrain the hypothesis space. Algorithmically, we're not going to allow everything to be considered. In the second one, when we start with a very constrained or somewhat constrained hypothesis space, we're going to think about, or we're going to seek flexibility by augmenting somehow the input as a way to add expressivity. And we're going to give an example of that later today. So in either case, once we make these assumptions, these decisions, we're going to look for algorithms that will find good hypotheses under some definition of good and hope that these will generalize well. Okay, so this is where I stopped basically last time, and I want to spend 2 minutes on administration. So the class now has officially 149 students. There are a few of you have received permits, so probably we'll have more than 150 if you accept the permits. If you have received one, there should be at least 5 of you. Please do it as soon as possible. The real deadline is today, midnight. Also, if you want to drop the class, please do it today so that we can act quickly and give permits to a few others. Now, it's not really the end of the world if you really want to take the class, and if a few slots become available, you can always petition, and if there's room, you will get in. But that's where we are. Now, all the people that get into the class, hopefully it's irrelevant to all of you, have to do homework 0. If you haven't, please follow the instruction on the website, send it to Dan Deutsch as soon as you can. Couple other things. So quiz 1 was out, was due last night. Hopefully all of you did it. It was easy. Homework 1 will be released next week. What else? Ask questions. And I'm going to say it many times. Please ask questions in class. Every question that you have, whether it's administrative or technical, half the other people have the same question or a version of it. So please ask. Another important thing is we don't have a class on Wednesday. Office hours are going to be as usual today, but I will not have my office hours on Wednesday. Questions? Yeah.
Is it possible to ask IT to allow us to download the class videos?
Okay, thanks. So first of all, you should know that there are videos online. Eventually, they'll move to YouTube. As far as I know, we cannot allow downloading it. We can just allow watching it, but I'm going to check.
You can allow downloading.
We can?
Yeah, all the classes, I've seen it in other classes.
Who said that? Oh, okay, you know.
I'll turn it on.
Okay. You see, you got your answer already. Thanks. Other questions? You see, every question has a good impact. Yeah.
Are there any updates on microprotocol?
So I think now it's a good time. If you want to do it, you have to complete a form and I'll sign it. You probably need to go to Nick in the academic office and get the form. Yeah.
Actually, I just emailed Nick and he switched me from before I finished no issue.
Okay. Without me signing, it's even easier. Yeah. Other questions? Yeah.
So what if I got information after the first quiz?
After the first?
After the first quiz, it's due last night.
We can solve this problem, but it's not a big problem. It's the quiz is half a point. We can allow you to do it. Other questions? Okay, so let's move on. So this is where we ended last time. Key issues in machine learning. So we always think about machine learning as algorithms, but I'd like to stress, and it will be clear today, that before we get to algorithms, we have to think about modeling, how to formulate a problem as a machine learning problem, how to represent the data, what learning protocol are we going to use. Representation, as you'll see, is going to be key. Both representation of the input, which we're going to call instance space, and representation of the output. What function do we want to use? What function space we want to use, and how do we want to represent it. And once we have these two issues of modeling and representation done, we want to think about algorithms. And even there, we have to think a little bit about what do we want from an algorithm? What are good algorithms? How do we define success? And it's a little bit different than algorithms that you've seen in other classes, because there is an issue of generalization, which is going to be key. And of course, the computational problem. We want algorithms to be efficient as a function of some of the important parameters. So let's start with the first real example. The example I'm going to use is that of context-sensitive spelling. You've seen the poem in my introductory class, and this is an instance of this. So what is the problem? Given a sentence, I don't know what the text shows is whether type 1 or whether type 2, to laugh or cry. Your goal is to write a program that, depending on which type of weather appears in the text, determines that it's correct or determines that it's incorrect and replaces it with the other kind of weather. So in this case, hopefully you would agree that the first weather is the right one. And the question is, how do we make this a learning problem? So we want to look for a function that takes as input a sentence that has either whether or whether in them, and maps it to the correct one. Right? So that's what we're after. A function from sentences to one of whether type 1, whether type 2. First question, if we want to define a function, is what's the domain of this function? Suggestions? Yeah?
Sentences that have either the word whether with an H or whether with an A in them.
Right, so that's the input. And in Piazza, there was a brief discussion of input versus instance space. So the input is clearly sentences, and I'm going to throw out all those that don't have any of these whether, so just sentences with whether type 1 or type 2 in them. But that's not enough for my function. My function is going to be evaluated on the instance space. So I have to map these sentences and encode them somehow so that my algorithm and eventually function can read it. What would be this representation? How do you want to encode the sentences so that your algorithm can look at it? Ideas? Yeah.
Maybe an array of words along with an index at which either whether or whether should be placed. That seems like a format that we kind of put.
So say it again. What do you want? You want an array.
Yeah, an array of the words in the sentence in order, and then along with an integer index at which the either whether or whether is placed.
So whether or whether is already part of the sentence. So you want to decide maybe to put 1 or 0 next to the word whether, so whether the one that appears in the sentence is correct or incorrect. Okay. So I encoded the sentence. Now think about it. I'm going to see many sentences. I need to encode it in such a way that I can learn from past examples. Right? So if I take this representation, which is a good start, every example, every sentence that I see is going to be different. Right? So how will I force learning to happen? Yeah? Okay, so now you want to encode the sentence not independently of other sentences. So first look at all the sentences that you see, do some counting, and then represent it. This will give me a chance that I'll be able to, I'm going to call it generalize, even though it's a very ill-defined word at this point. So I'm going to do something like this, but I'm going to start with an even a simpler representation. So I know that in the course of observing many sentences, I'm going to see many words. Maybe I'm going to see 50,000 words. So the way I'm going to encode the sentence says is I'm going to invent Boolean variables. I'm going to call the Boolean variables xw, x subscript w, and this is going to be representative of whether I've seen the word w in the sentence or not. So rather than having a short array, I'm going to have in principle a long array of size 50,000, and every sentence is going to be encoding as ones those words that are present in it. That's it. So I have a set of 50,000 Boolean variables, one for each possible word, and in the sentence I don't know whether to laugh or cry. 1, 2, 3, 4, 5, 6, 7, 8 of them are on, and the 50,000 minus 8 are off, are 0. That's my encoding of the sentence. Is this a good encoding? Do I miss anything? Yeah,
You don't lose word order.
I lost word order. Yes.
You also lose the number of times the word appears.
If a word appears multiple times in a sentence, I lost it. So you can improve. I can encode positions, I can encode maybe number of times, but I'm just being simple here. So at this point, what I did is I took every sentence and mapped it to a 50,000 dimensional Boolean vector. Right? Some of these vectors, some of these points are weather type 1 points, some of them are weather type 2 points. So now I can do the counting that you wanted, because when I look at many examples, I can look at dimension 7, and I can see, well, dimension 7 always represents the same word. Right? I don't know which word it is, but I decided ahead of time on some order of words. And I can see how many times this dimension is active in weather type 1 words or in weather type 2 words. So it facilitates doing this counting. But more importantly for now, I defined my domain. So this was my modeling step, right? So I took a problem, or we are still in the modeling step. I took a problem, context-sensitive spelling, with respect to a specific pair of words, weather, and I'm in the process of making it a learning problem. So what kind of learning problem will it be? Or before that, input instance space. So my input here is sentences that have weather. I converted it to my instance space, which is a 50,000 dimensional Boolean vectors. That's my instance space. That's what my function are going to see. That's what my learning algorithm is going to see. So what kind of learning problem will it be? Even before we know what is a learning algorithm, what is the protocol? I mean, what kind of information do you have? So before we talked about supervised learning, right? We said that we're going to give the learning algorithm inputs, x's. In this case, these are the 50,000 dimensional vectors, and labels. What are the labels here? The type of weather that I've seen in the sentence. So, is this a supervised learning problem? It is, because that's how I describe it. I have pairs x, a vector that encodes the sentence, comma, the supervision. Where do I get the supervision from? So think about, really, you have this problem. Yes? So one suggestion is the input is labeled, so which means that you hired someone to take a lot of sentences and tell you what's the right spelling. Yes?
You can also scrape the web for articles and find any sentences containing either and then just take it for granted that's the correct way.
So here is a way to avoid hiring someone to supervise you. Basically, I'm counting on the New York Times. I'm going to scrape the New York Times and assume that they don't have a lot of spelling mistakes. So whenever I see whether type 1 or whether type 2 in a sentence, I'm going to assume that's the right spelling. Now, I do have label data. So we can resort to your setting of the problem, only that I didn't have to do the work annotating the data. And that's a very important observation. So basically, all we know in machine learning is to do supervised learning, which means we always want to give to the learning algorithm label data. X's, comma, Y's. Input, comma, labels. But it doesn't necessarily mean that we always have to sit down and label a lot of data or hire people to label a lot of data. Quite often, we can make these clever observations and say, you know what? Here is something here that is quite correlated with the labels that we care about. The New York Times has mistakes, has spelling mistakes, but you know, it's going to be very tiny relative to the number of sentences I'm going to get. I'm counting on it to not affect my learning algorithm. So it's supervised learning, but we didn't have to work for it. So this is an important lesson for us to keep in mind, in general, outside this class also. And the final question I want to ask, okay, so we have a learning problem now. What's going to be our hypothesis space? That is, what is the set of functions that we want to learn? Any idea? How would you do it? Yeah.
Some type of function that would give like a probability on which word would be better fit in the sentence, or whatever.
Okay. So a function that gives probability to whether type 1 or whether type 2. But at some point, we need to commit to the functional form of this function. Because, you know, our learning algorithm needs to know, what am I looking for? It could be just a set of rules. If you see the word this in the sentence, say this. If you see that word, say something else. If you see this combination of words, say this. Or it could be another representation, but we'll have to commit to a function space. So let's think a little bit about it. So this is the problem that I have, right? So I have my feature vector, my vector space, sorry. It's a two-dimensional space here because I don't know how to draw 50,000 dimensions. But basically in this vector space, I threw whether type 1 and whether type 2, the purple lines and the red points. And what I want to do is I want to separate between them somehow. I want a function that says this is whether type 1, this is whether type 2. And I want a function that separates it best, under some definition of best. So what about this function? It's a good one. Here's another one. Many options. So I have to think about what function, I have to think about what's best. Which one would you choose among these functions? Which one? Blue one. Everyone agrees on the blue one? You agree on the blue one? The green one looks better. It overfits. So the green one is perfect here, but you have some suspicion that, given what we talked about already in the class, that it's too complex. It can do whatever you want. But we have to say something like this in a more explicit way. So clearly you see that there is an issue of memorizing here versus learning, or accuracy versus simplicity. We also think about, when we ask the question, how well are we doing? How well are we doing on what? We actually don't care about this data that I showed here, because this is our training data. Well, we don't really care about it. To some extent, we may care about it. But you already know that you can do well on your training data. Someone gave you the labels, or you figured out how to get the labels. You really want to be able to generalize, and you want to think about whether the green function and the blue function are going to give you better chances to generalize. So, of course, we have to attend to how to find it, but before we do this, I'm going to define the learning problem in the following way. Given that you chose the blue one, I'm going to say, you know what? Here is my learning problem. It's not find a function that best separates the data, but rather find a linear function that best separates the data. What do I mean when I say linear here? Linear in the feature space. So if X is my data representation, in this case it's this 50-dimensional space of Boolean features, and W is going to be my weight vector, the linear function means that I'm going to make a decision based on looking at this dot product, W transpose X, and I'm going to take the sign of it. That is, whether it's positive, I'm going to say whether type 1. If it's negative, I'm going to say whether type 2. Explicitly, this is the function I'm looking at. You know that already. You did homework 0. This is the dot product, and by sign, I mean sign of Z is 0 if it's negative, otherwise it's 1. So that's the set of functions that I'm looking for. Is this good enough? Well, clearly, many functions are linear functions in the feature space. For example, we talked about conjunctions, right? You thought about it also in the quiz. Here is a conjunction. I claim that this is a linear function. What do I mean when I say that this is a linear function? So these are Boolean features, just like in the example that we have. So x1 is 0 or 1, x3 is 0 or 1, and so on. What do I mean when I say that this is a linear function? I can find a set of weights, W, and in fact, I care also about theta because I want to shift the function away. Oh, that's important. I care about W and I care about theta, and I want to find W and theta that will behave like this. Any suggestions? How can I write this conjunction as a linear function? Yeah.
x1 plus x3 plus x5 minus 3.
Okay, so you suggest to take W1 being 1, W3 being 1, W5 being 1. All the other W's are going to be 0. And theta is going to be 3.
Negative 3.
No, 3 because I wrote minus theta
Oh,
there.
yeah.
So this is your suggestion. So this is the weight vector, 1, 0, 1, 0, 1. I'm assuming that it's only 5 dimensions here. Theta is 3. Now notice that if you take this function, every x, vector x of 5 dimensions that you feed into it, and you evaluate this function or evaluate the conjunction, you're going to get the same result. Agreed? So we proved that this is a linear function. It's important to know because we're going to deal a lot with linear function. You want to know what kind of things can be expressed. In fact, it's even more expressive. You can take a function like at least m out of n. Remember that we gave this example last time. At least 2 out of x3, x1, x5. This is also a linear function. Suggestions? Again, you have to give me a weight vector. Yeah?
You first write as a conjunction, and then from that we saw that we can...
Can I write it as a conjunction?
like it's a conjunction and a disjunction.
Okay, but that's a good idea. You're right. I can write it this way. Not going to help me to make it a linear function for a reason that we'll see in a second. Yes?
Use the same W, but theta equal to 2.
Okay. So again, I'm going to put 1 on x1, x3, x5, change theta to 2, and now what I'm requiring that at least 2 out of these 3 is going to be 1. And again, if you think about it for a few more seconds, you'll convince yourself that these two functions are the same function. They're just represented differently. So we show that this is a linear function. Now, not everything is linear, but probabilistic classifiers, for example, that we're going to get to in the second half of the class, even though they don't look like this, actually they are linear classifiers. So when we play with linear classifiers, we're not making huge mistakes. This is a really expressive class of functions. But not everything is linear. So you can think about XOR. Some of you have seen this function, XOR. I show it here for two variables. That means x1 and x2, or not x1 and not x2. Not a linear function. In the space of the x1, x2, you cannot write it as a linear function. And many other non-trivial DNF. You know what a DNF is now? Disjunctive neural form. You can see it here. It's not a linear function. And therefore, your idea, as is, wouldn't have worked, because when you convert it to a DNF, you don't know, is it a simple DNF that can become a linear function, or a non-simple DNF that cannot become a linear function? Just distinguishing these two is not an easy problem. And therefore, we don't want to go through the DNF route, even though on the face of it, it makes sense. So not everything is linear, but it can be made linear. And that's another important lesson that we already get today for machine learning in general. What do I mean when I say can be made linear? Let's look at this example. I have blue points and red points. These are my inputs. And I want to learn a function that splits, distinguishes blue from red. I like blue, I don't like red. What will be the function that's doing it? So you can clearly see that the way I represented it here, it's not linearly separable, right? I can separate it, but I need a complex function to separate it. But I can make it linear. What do? I took the x value and squared it, and I plotted the same points in the space x, comma x squared. I didn't add any information, right? The information was there already. This is the space x. This is the space x, comma x squared. But now I can separate it with a linear function. So it's magic, right? So I did not have add any information. What I did is I changed the feature representation, and now the function is linear. So this is an important lesson that shows that representation is really key. What features you use is really key. Computationally, we're going to talk about it later in the class. There are multiple ways of doing it, some explicit, some more implicit. But the fact that we can do this is really important. You can do the same thing for XOR. You can invent a new set of features, and now XOR in this new space will become linearly separable. Here is an example. So I gave the example of a non-trivial DNF. What is a non-trivial DNF? Here is an example. X1, I'm not writing the conjunctions here. I'm just leaving it as a product. So it's X1 and X2 and X4, or X2 and X4 and X5, or X1 and X3 and X7. Complex function. Think about it as this kind of curvy thing on the left that separates whether type 1 from whether type 2. I don't know how to learn this function, or I don't want to try to learn such expressive functions. What will I do? I want to make it a linear function in a completely analogous way to what we've done before. I'm going to invent new features. What will my features be? For each conjunction, x1 and x2 and x4, x2, x4, x5, and so on, I'm going to invent a feature. Now, of course, I don't know exactly what's in this function. This is hidden for me. So I'm going to invent a feature for all conjunction of size 3. So I'm going to move from this space of x1 up to xn to this new space at the bottom here. Each y here, I'm calling it y, is going to be a conjunction of size 3. If I started with a feature space of size n, what will be the size of my new feature space? Yeah.
What we're saying here is like each one of these disjunctions is one function. We have y1, y2, y3, so then each one has its own dimension, and then we're plotting the points on those 3 dimensions.
Right, but I don't know ahead of time that the target function is this x1, x2, x4, or x2, x4, x5, and so on. So I need to entertain all possible conjunction of size 3 as my features. So if I started with n features, x1, x2, x3, up to xn, now my feature space is going to be x1, x2, x3, x1, x2, x4, x1, x2, x5, x1, x3, x5, and so on. All conjunction of size 3, each one of them is going to be a feature. How many will there be? N choose 3, right? I have to choose 3 variables out of the n, conjoin them, this is a new feature. So my new space y here is of size n cubed, so I blew up the feature space, but now this same function that is so complex there is a very simple function. Maybe it's y3 or y4 and y7, and this is a linear function. We showed a couple of slides ago that conjunctions are linear functions, but for the same price, these junctions are also linear functions. So what is the lesson here? What we showed is that even though we're dealing with linear functions, which we're going to do for a large part of this class, it's okay. Even if the function you're after cannot be represented on the face of it as a linear function, you can always do something by increasing the dimensionality, by adding more features, so that linear is going to be okay. And that's important because we'll see that it's easy to learn linear function, or easier to learn linear functions, and a lot of what we're going to do is going to play with this. Okay, so I want to give now an example of a concrete example of the stuff that we've talked about already, and I'm going to give you, okay, before that, I'm reminding you, I don't know if you can read this, that I asked this question when we talked about in the first class on the example of email, and I gave you suggestions for features. One feature was, does this email contain the word class? A second feature was, does this email contain the word waiting? And the third example was, does this email contain the word class and the word waiting? And I asked you then, is it the same? And we kind of agreed that I did not add any more information because the first two features, class and waiting, already have the information of class and waiting. But hopefully, this example that I showed now convinces you that there is a difference. Because in terms of the functions that you will learn, function that will express the mapping from the email to the decision, the folder it's going to go to, it matters whether you just look at, is the word class there, is the word waiting there, or are both there. The overall function could be simpler if you have these conjunctive features. And let's look at what do I mean when I say real features. So I'm going to take this example of weather, and show you real data. So it's on the web page. If you click on it, you will see it. Let's see if I can show it to you. Can I? Okay. Let's try this. Okay, doesn't allow me to move to this. What's happening? Okay, we're stuck now. Now I'm trying to move to the screen. Okay. No. No, this screen is stuck. This one is okay. No. Sorry. Okay. Okay. Okay, so we're not going to see the web, but you can click on it, and I'm going to see you the main thing I want you to see here. Okay, so okay, so here is what you're going to see there. You're going to see files of 4 types. Yes.
I have a question. Will adding another feature make it harder to find a linear separation? And if so, how do you determine which features to add?
Okay, so I don't know what you mean when you say how.
Because in the previous slide, you showed that if you added a feature, it would make it easier. Since you change from 2 dimensions to 3 dimensions, you can find a linear separation easier. But are there cases where if you add a feature, it'll bring them closer together?
Okay, so let's take this example here. When I give you the data this way, for each point I give you its x value, there's no linear function that separates the data. If you want to learn a separator, your hypothesis space has to be larger than that of linear functions over the x. Once I change the representation to x comma x squared, now there is a linear function. So the first issue is existence. Can you express the function that you care about, the function that separates the data, linearly or not? There is a question of how difficult it's going to be to find this function, which in our case it's going to be typically a function of the dimensionality and how well separated the data is. But really, by adding a dimension, all we do is we improve the separability. We never make it worse. So from this perspective, it's going to make it easier. From the dimensionality side, it's going to make it harder because you're going to deal with more dimensions. And we'll see what will quantify the impact of each one of these. Yeah.
You said before that you can always expand the feature space and then apply a linear classifier to that. Is that just something that you can try in general, or has someone actually proven that for any given problem you can always expand the feature space?
So for every Boolean function, I can always expand the space, but sometimes I have to expand it exponentially, which means I'm moving from, say, a feature space of size n to feature size 2 to the n. I typically don't want to do that. However, if I have to do it this way, probably no one else can learn this function in any other way anyhow. But we're going to get to talk about kernels, and then we'll address this issue in a more, in a clearer way. So it's always possible, and in realistic cases, you never have to go too far, because the functions that we care about are simple, under some definition of simple. So, so it's true that all Boolean function can be linearized, as I said, but it's just a theoretical response, because in the limit, that means exponential feature space. So what I want to do is I want to give you a concrete idea of a feature space. So this is the problem that we care about, whether. If you click on this, you will see many problems of context-sensitive spelling. Scroll down, you will see the whether problem, and you will see a few files. Just a second. Files of text, just the way it is. Sentences that contain either whether type 1 or whether type 2, and then a few other files that, when I converted the input space into feature spaces, and I'm going to discuss this now, how this is done. Yes, question, Tel.
I was wondering why on the last slide, they're in like 2 dimensions.
Here? I don't know how to draw it in more dimensions.
I thought it was like one,
So they are really, the left one is n-dimensional, because I wrote the space is x1 up to xn. And in the right, it's n-cubed dimension. But I don't know how to draw it in a better way. So really what I wanted to impress on you is on the left, it's a smaller dimension, and the function is more complex. On the right, it's a higher dimension, and the function is simpler. You see, it's a kind of a plane in this space. Okay. So I'm talking about whether. I'm defining features. So the features are really the input that the algorithm sees. The algorithm does not see the sentence, I don't know whether to laugh or cry. It sees some representation. So in this case, the features are going to be a little bit more complex than what I showed before, which is the XW. If the word is there, put 1. If the word is not there, put 0. I'm going to define 4 types of features, really. And here is my notation here. So I'm sitting on a word. I'm sitting on the whether type 1 or whether type 2, the target word, I'm going to call it. And then I'm going to open a window around it and represent only this window. Essentially, I'm not going to represent the rest of the sentence. I'm going to represent only a window around the target word, plus or minus 2 words around it. Okay? That's going to be my example. So my algorithm doesn't know about the sentence, knows only about, here's the target word, here is a window around it. That's what you see. What do we see really? We see relative position. I'm going to denote it as +1 or -1, whether it's before the target word or after the target word. I'm going to see either the word that is in the sentence or its part of speech tag. I'm denoting this by P here. How do I get the part of speech tag? Doesn't matter. Someone told me. So that's one feature. For example, look at the first row here. 1P means that the word following the target word has a part of speech determiner. 1W means the word following my target word is the word the. -1P means that the word before the target word is a punctuation, and so on. So these are 2 types of features. Before and after, what is the value of the word there and what is the value of the part of speech there. This gives me 2 types of features, 1 and 2. Feature type 3, conjunction of size 2. For example, look at this row here. it says minus 1p equal v, which means the part of speech of the word before my target is a verb, 1p that, and the word after me is a determiner. Another example, let's look at a more interesting example here. Can you see this? Do you see my mouse moving? Yes, you do. Okay. So this says the word before me has a part of speech verb. The word after me is the word D. So this is how I represent the sentence. And then I have a fourth feature, which is just the word W occurs in the window of plus or minus 2 around me. For example, the word not, or the word or. So this is my encoding. So I have a lexicon of features, of 4 types of features. Now, whenever I see a sentence, I see which of these 4 types fires in the sentence, and I write it this way. So given this, what you see here on the left is something that happens before I see any text. Once I see text, I evaluate this and I get these things. So this is an encoding of features that I've seen in the data. What you really see here is the definition of the feature on the left. You see some statistics that you don't care about. It's really chi-square, but it doesn't matter now. And then you see 2 other numbers that I put here for your information. And this is how many times I've seen this feature active in a weather type 1 example, and how many times I've seen it in a weather type 2 example. Yes?
What's the difference between 1P and 1W?
So 1P means the word after me has the part of speech that is the determiner, for example. 1P, let's look at the top one. Now, this, and 1W means this is the word that appears after me. Now, there are multiple determiners. The word A is also a determiner. So this feature is going to fire only when I see the word D. This feature is going to fire when I see the word D, but also when I see the word A. Okay? So it gives me a little bit of abstraction over the representation. Okay, so again, we want to distinguish here between feature types. I only have 4 feature types, but I have many, many, many features. Whenever I see a sentence, the feature type, what is the word after me, gives me a different type of a different feature. Right? So again, let's go to this sentence. Where am I? Okay. I don't know whether to laugh or cry. When I see this sentence, the feature that will fire is 1W is 2. Also 1P is a preposition. Minus 1W is no. Minus 1P is a preposition, is a verb. If I see I don't care whether to laugh or cry, still I'm going to have 1P is going to be 2, 1W is going to be 2, 1P is going to be a preposition, but minus 1 no is not going to fire in this sentence. Instead, minus 1 care is going to fire there. So every sentence, different features are going to fire, and they're going to give me the representation that the algorithm sees. So what will the algorithm see? So first of all, I generated this list of possible features. As I said, I also included some statistics on the right, but this is just for my information. It's not part of... and then, when I see a sentence like this, but whether the murder of something happened, I'm going to convert it into these features. Each feature is going to get a number, for example, rather than writing it as a string. And this sentence is going to be converted to this example. Where in this example, what I encoded here is the first number is actually the label, 1 or 0. Whether type 1, whether type 2. And the rest are indices of my features. So these are all the features that were active in a given sentence. So notice first that if my feature space is of size, say, 100,000, really what I have here is a feature vector of size 100,000 with very few ones and the rest zeros. Because the number of ones really is a function of the length of the sentence or the window that I opened around the target word. And then most of the features are not going to be active there, right? So they will be 0. Yes?
Just to be clear, so for example, the last number in the first row, 1,176, that's the index of the word in the English language that takes that?
That's an index of the feature in this list. So these are the features that I have. 1p equal determiner is my feature number 1. 1w equal d is the feature number, sorry, this is 2. I don't use 1. This is 3. This is 4, and so on. And then every sentence is encoded as a list of the features that are active in it. Now, I could have written you a vector of size 100,000 with a few ones and many zeros. Instead, what I did is I chose to represent it in a sparse way. So I only listed those indices that are 1 in the vector, which makes more sense, right? As computer scientists, this is what you would do. You don't want to carry all the representation. You'll just, because you know that very few of the indices are going to be 1, you're just going to list those that are 1. Okay? So is it clear why I want to use a sparse representation? Now, this is the test data, what I'm showing you here. Why do you see variable size examples here? Yeah? Sentences of different lengths. That's one reason. But I mostly look at a small window, fixed size window. So you're right, but almost right. Yes?
It also depends on the position of weather.
If the weather is the second word in the sentence, on the left I'm looking just at one position. If it's the fifth word in the sentence and there's a lot to the left and the right, I'm going to have more window, more stuff in the window. That's one reason. Yes?
Some of those features are overlapping, so certain sentences might activate more features than other sentences even if they're the same type.
Right, but here I'm talking about a given sentence. So why is the first sentence of size, 20, and the second one of size 30? So, as I said, this is the test data. My lexicon was generated based on my training data. It could be that in the test data, there are words that I've never seen before, which means they are not in my lexicon, or the corresponding features are not in my lexicon. Right? So maybe I see now a sentence, I don't care whether to cry or laugh, and I've never seen care before. So the feature -1w equal care is not in my lexicon. So if I haven't seen something before, I will not know. And going back to the question that you asked about why do I do W and P, this is an example where if I've never seen the word care before, I will not have the feature -1 care, but I will have the feature -1 verb, because I've seen many verbs before the target. So it will still support generalization. So this has to go with how we do feature design, which I'm not going to get into. I just want to get to the mechanism of what we are doing here. Questions?
What is the number of zeros stand for?
Here?
No, in the, there are many zeros. I'm not sure.
Oh, here, the first numbers. So the first number is the label. The way I encoded it is the first number is always the label. 1 means whether with H, and 0 means whether with E. And then I'm putting there all the indices of the features. So each row here is a sentence, an encoding of a sentence, and that's what my learning algorithm is going to get. Now, of course, you can replace each number here by the string from the lexicon that I showed you before. It's just going to take a little bit more space, so I didn't want to do it. But each number here, 198, represents a feature from this list. Question?
Where does the word type go into that? Like adjective or
How do I know that?
also like how are you including that?
So I encode it this way. I'm just saying 1P is a determiner. And then I call this feature feature number 2. And here I say -1P is a punctuation mark. And I call this feature number 5 and so on. How do I know it? Someone told me. So when I saw the sentence, I also had a function. So I need to have a function that takes the sentence and converts it to these things. Inside this function, I also encoded the knowledge of what is the part of speech tag of each word, which is not a trivial problem in itself, but I'm assuming that I have some box that knows how to compute it. Yeah.
So in the slide representation 3, that's the test data. That's how you represent the data to the learning algorithm.
Yes.
Then it encodes it with the schema in representation 1, and then makes a prediction.
So already hidden here is the representation 1, because I'm consistent about the numbering scheme. When I say feature number 3, it's always the same feature there. And this is what the learning algorithm sees. So the learning algorithm is going to see, for example, it may figure out that if you see features 3, 11, 92 on, it's always weather type 1. And if it sees, 1068, 1142, 1207 on, it's always the other type of weather, and so on. That's what my learning algorithm eventually will find. But I'm just talking here about the representation or the modeling. So we always have to take data that looks like, real world something, sentence, image, or something like this, and convert it to a feature representation, which is the exercise that I've done here. So think a little bit more about it, try to make sure we understand it. In fact, you are going to do something like this already in the first problem set. Yes?
So we talked about like variable size of each set of features. Is it like, is it necessary to keep the size like equal for each set?
Okay, so there is an implementation issue here. Many learning algorithms, the way they've been implemented, they always like to see fixed size vectors. And this will be the algorithm that you will use, for example, from the Python library. So, yes, you'll have to do something, and you'll keep it in a fixed size vector, which will be a little bit wasteful, but there are some tricks, implementation tricks that will deal with it. So here I wanted to really send the message that really you have variable size vectors. And the reason you had variable size vector, and this is a phenomenon that you will see also, is that when you train your model, when you generate all the features from the training data, you have a fixed size lexicon. These are all the features that I've ever seen. And then when comes test data, you see new things. It could be that you have never seen some things, and therefore you will have less active features. So this message hopefully is being sent in a clearer way when you see the variable size. Had I shown it to you in a fixed size vector, first of all, it will be longer. Second of all, you will have to count the number of ones to send this message. Okay? Okay, so now we're done with representation, everything is fine, and we have to learn. So, and the question for us is how to learn. So here's the problem now. We have 5 minutes, so at least we can introduce it. I took the examples and I mapped them into a vector space. Again, whether type 1 are purple, whether type 2 are red, and I want to find this linear function. We agree that we're going to search for a linear function. How do I find this linear function? What is a linear function? Really, it's a weight vector, W. So I'm searching for a weight vector W of the same dimensionality as the data representation. I don't know, 50,000. How do I do it? Suggestions? So think about it this way. All you see is you see the points. You don't see this hyperplane, this linear function there. Your goal is to place a linear function in this vector space so that it's doing a reasonably good job under some definition that you will come up with of separating the red from the purple. What would you do? How would you determine or find this linear function? Yes?
Draw several lines and then analyze it every time it gets one on the wrong side.
Yeah, excellent. So try, right? So let's put a line and see how well it's doing. What does it mean, how well it's doing? Let's assume that all I'm going to do is I'm going to count how many purples are on this side and on that side, and how many red are on left side and right side. And I'm going to penalize it based on how much does it violate what I want. I want all the purples on one side and all the red on the others. So I tried. If it's not perfect, I'm going to change it somehow. I don't know how, but we have to come up with a policy of changing the line. Let's see how well we're doing now. So we're going to have some kind of a search algorithm in this space of linear function, and this search is going to be driven by how well we're doing. We're going to stop it once we're doing well. So basically, it's going to be a local search algorithm. We're going to start with one linear function, see how well we're doing, correct it, we have to figure out how to do it, and repeat until we converge. Very simple algorithm, very general algorithm. And the only thing is, well, first we have to realize that it's not the only way. We're going to see later in the class that there are some magical way where you just look at your data, compute something, and boom, you have a linear classifier. No search at all. But in general, the algorithm is going to be a local search algorithm, and we'll have to, for each one of these points, how to start. That's going to be easy. Let's say we start randomly. Choose random W, and that's it. See how well we are doing. We have to figure out what does it mean. Correct. We have to decide how do we correct, and then we're going to repeat. So the first thing we're going to attend to is see how well we are doing. And we're going to talk about it next time, which is going to be next Monday, about these two things. And we'll basically give a generic learning algorithm that is going to stay with us for the whole class. Okay, see you next time.
How many people are? How many permits do you think are gonna get?
I'm probably going to give just a handful more. You did not receive one.
No. I've been to every lecture and I've done
So did you send me email? Send me email. I will have a few more slots because I assume that today people will drop it. As I said at the beginning of the class, even if you don't get it today, there will still ways to get petition because people will leave the class. But drop me an email so that I know that you're interested and you want to return. Same thing. Send me email. I'll keep the people that survived. Today is Monday. Try to do it quickly. Did you register already?
Yes, I just.
So try it and see that. Do you understand this conjunction? If I give you a vector, of Boolean vector, you compute, you evaluate it on this conjunction and you get either 0 or 1, right? So when will you get 1? You'll get 1 when x1 and x3 and x5 are 1, otherwise you'll get 0. The same thing is going to happen with this linear function. The only time you will get 1 is if x1 and x3 and x5 are going to be 1. If one of them is not 1, you'll not reach 3. If someone else is 1, it doesn't matter because the weight of the other x's is going to be 0. Okay? So make sure that you understand each one of the functions and then make sure that you convince yourself that for every input, they're going to behave the same. Got it.
Yeah, thank you. So just catch up.
Try to do it as quickly as you can. And quiz 1, we'll figure out the solution.
Should I send an email to let you know that I had a meeting or
Yeah, you can send me email on quiz 1. But homework 0, just do it as soon as you can, and there's an email on the website. You have to send it.
Okay, great, thank you. Last thing, I'm going to be missing a couple classes
Wednesday is Yom Kippur. Oh, you didn't. Okay. But follow the videos. Yeah.
Great, thanks so much.
Yes, so that means the relative position is plus 1, which means I'm after the target word, and after the target word, there is a determiner. Determiner is a part of speech. It's like D or A.
Oh, so that represents
Determiner. Yes.
so then what does it
So if you go down the slide, you will see that means this is some statistics. You don't care about it. This is a chi-square statistic of the features. It doesn't matter. This represents that these specific features appear 0 times in weather type 1 examples and 34 times in weather type 2. And if you go to the website that I pointed out in the previous slide, you will see all the explanation.
So what does this W, 1W?
1W means here, relative position is +1, and the word W is there. So W here is the word D. So after the target word, the word D appears.
After the, so W, so what the W key, what's the difference between W and P?
W is a word, is a power speech. It's either a noun or a verb or an adjective or a determinant.
Alright, thank you.
So as I said in the class, you can still petition after that. Yes. Hi.
Hi. Just wanted to say that.
Okay.
But you mind?
Yes, thanks. Did you, have you been here before? I mean, I haven't, okay, yeah, that's too easy.
Yeah.
Okay. So again, as I said, it's the last day, but people will be able to petition later if someone goes to class, which will definitely happen. It's not. Yeah. So as of today, there are, as of noon, there are only 149 people registered. So technically, there's one slot, but there are more than 5 people that have permits to register, so we need to wait for them. Yeah. So we'll see. Did you send me email about the class? What's your name? Remind me your name again. This weekend? This. Okay. you do? Yes, sorry.
Questions. So what is this conjunctions besides two?
Go to the list.
This one?
Yeah, so, this is the conjunction. It means minus 2W is true and minus 1P is V. So it's both of these conditions are happening. This is a conjunction.
Oh, so it's like combining these two features together. So why sometimes it's negative 2W, sometimes it's negative 1W, sometimes 1W?
Because as I said, the window is plus or minus 2. So sometimes the word, so I encode word that appears before, minus 1, and 2 before, minus 2. To the right,
Then
1,
you
to the
should collect 4 words, right?
I collect 4 words.
So why here only choose to show one or choose two?
No, all of them are encoded. Each one shows one of them.
Oh, so this is like a very tiny piece of the code, right?
No, this is everything that you see in all the data, in many sentences. You've seen
For
at
every
the
target
terminal,
you find, right?
for every target that you found, you extract features. And this is the compilation of everything that you've seen throughout the data.
Okay, I see. And how can we know that whether this is the first target and then the other is the second target?
Here you cannot tell. This is just features.
We cannot. Okay. So here is just extracting all these features.
But here you can tell. Here I tell you
try
which
shift
features
refreshing
are
if it looks
active.
too
One in this example. This is the one example. This
Yeah,
is the
shift
zero
refresh
example.
the page, see what it looks
zero
like. It shouldn't be there.
So for now, I'm still on wait list. I'm seeing that it's a little opportunity for me to register for this course because I'm on a character 5. So I'm asking probably just for auditing in this course.
So drop me an email.
I do email you that.
Yes.
Like,
So auditing
yeah,
is not a problem. I mean, you can always audit the class.
That's great.
I don't
But
have any.
I need you, if that it's okay, I need you to add me to the canvas so I can access all the
You can access everything.
the videos.
Yeah, so again, I talked about it in the class multiple times. Everything is open.
But I'm not on Canvas.
Doesn't matter. The class is open. Everyone. No, you cannot be on Piazza.
So I can add me myself on the Canvas?
You don't need to be on Canvas. All the material is open.
So where can I find the link for the videos?
Go to the website.
The CIS 519 website?
Yes.
Okay, I will check it. Thank you, Professor.
What do you mean? I didn't understand the output space.
The output space is 0 and 1.
Okay, just 0 and 1 in this case. It wouldn't be the combinations of, like for this one, it wouldn't be the different combinations of this row.
No, the output space for each example is either 0 or 1. Yeah, so the space is just Boolean. Each example is one of them. Sorry. Yeah. Yeah, go ahead. So you see, the space is just Boolean space.
Regarding this, it's 320. Signature.
When did you send the email?
Earlier this morning. This is CS220, right?
This is not CS320. This is CS460.
Alright.
320 is